Hi, today I'm going to talk about building a do-it-yourself pitot tube which can be used to measure airspeed. This kind of airspeed is called indicated airspeed because that's the airspeed that is measured directly by this pitot tube instrument, and that can be used to then calculate other airspeeds for aircraft or even for terrestrial vehicles if you plan to do that. So the main equation that is used to do this is Bernoulli's equation, which states that P static, which is the static pressure, which is the air around us, plus the P dynamic, pressure dynamic, is equal to the P total. So in this instrument here, the air that is impinging upon this small orifice over here creates the dynamic pressure, and basically when you add that to the static pressure in the atmosphere, you get the total pressure. So P static plus P dynamic equal to P total, which is equation number 1. And you can basically break that down into components, which is P static, which is the pressure that is measured using a barometer or anything like that, plus this equation, this term, which is rho times V squared over 2, which is dynamic pressure equal to P total. So P dynamic is really P total minus P static. So where rho is here the density of the air around us, and V squared, V is the velocity of the air that is hitting the pitot tube, and the constant 2. So essentially, if you know rho and we know the static pressure and total pressure, we can essentially get the velocity. So the total pressure minus the static pressure is then sent to an instrument like the airspeed indicator, which can then directly read out the velocity if calibrated correctly. So velocity then turns out to be square root of 2 times P dynamic minus P static over rho. So this is directly computed by the airspeed indicator, and these two constants can be plugged in and calibrated to get the right airspeed. So a couple of things one has to keep in mind. The indicated airspeed is essentially the raw airspeed that is measured by this instrument, and it is typically for, if you're at sea level, this will be equal to the other airspeeds shown over here, calibrated or true airspeeds. Calibrated is really more like an instrument error, or due to the way the instrument is located, or where it's if there's any errors in it for offsets or anything like that. So that is a calibrated airspeed. So it's just a variation of the indicated airspeed with some additional terms or corrections applied to it. It doesn't really take into account anything like the actual pressure of the atmosphere or the temperature of the air. So the true airspeed is really the corrected airspeed, indicated airspeed or calibrated airspeed corrected for pressure and temperature. And as you go higher in the atmosphere, or if you go to higher elevations, this true airspeed will actually be a larger value than what the indicated airspeed is, because the air molecules at high altitudes is thinner, the pressure is lower, so you get a slightly reduced indicated airspeed as you go to higher altitudes, and that is essentially, you can say, approximately equal to 2% decrease in airspeed for every 1,000 feet of increase in altitude, roughly. So, and that is essentially taken care of by the airspeed instrument, also in many cases for aircraft. So for terrestrial applications, which is what I'm designing, this DIY tube is for to measure airspeed for cars at typically sea level. I'm not talking about Denver or some high altitude areas where you would have to correct that to get the corrected indicated airspeed to the true airspeed, which will be significantly different at higher altitudes. So I'm going to focus on the building of this thing and do some measurements in a car, and then see what comes out of it. I did build this tube, this pitot tube, and compare it with a commercially available one, which is fairly cheap. You can buy those on Amazon or other websites which are used for measuring airspeed of drones or hang gliders and so on. So this is a low speed instrument, really not meant for anything beyond 100 or 150 miles per hour kind of applications. So here's the construction of this pitot tube itself. It's very straightforward. I got some ideas from a site on the internet. I think the website is called Instructables or something like that, and they had done something very similar, and I basically followed their procedure. Did some minor changes to the procedure because in that design they had this big tube actually bent, and I didn't know, I couldn't bend this very well, so I was afraid I would kink the tube and do some damage. So what I did was I cut it roughly as shown here to get a roughly 45-degree angle on the big tube, which is about 7 or 8 millimeters in diameter. It's not critical. Um, but what then I essentially, once I got this soldered and brazed, basically copper tubes, I then drilled 4 holes around about, this is about 2 to 3 centimeters away from this point over here. So you drill 4 holes around this thing to get the static pressure, which is then picked up by this tube and then sent to the ASI, the airspeed indicator, which is shown here. Then I drilled a hole on this side over here carefully, and then I threaded or pushed this 2 millimeter tube all the way across to the end, and then I inserted some wiring, some small wire like a copper wick, which is then wrapped around here and then soldered to basically block and to center this inner tube into this bigger tube. If you don't do that, this thing will rattle around or it might not seal properly. You don't want any air coming into this static portion over here from the front. That will basically decrease your reading. You want this to be absolutely still air as far as possible. One thing people do is to make some kind of a shape to make this a gradual slope over here. I think that might affect some of the turbulence around this area, but I haven't done that yet, but I'll maybe do that later. So you can put in some like a plastic or some epoxy and just make a shape that is triangular to smoothen out this edge over here. And then on the other side, this small tube is then, I somehow crushed this bigger tube here and I fitted it over here and soldered this thing, making sure that this is also a tight connection, because the main total pressure is all the way through this red tube here and goes to the ASI. So this is the one that is, you shouldn't have any losses or any errors in this one. The static pressure is somewhat easier to handle. It actually is picking up just a still air pressure around this instrument, which is got no dynamic pressure in it. So then these two tubes are then with the polyethylene tube. I managed to hook it up to the ASI, and then the main thing is how do you install this in your vehicle. So you can try various things, putting it out of the window and then running tubes and then making sure you can close the window partially, and especially if you're driving at freeway speeds, and then making sure you don't crush the tubes, these two tubes coming into the car, into the ASI which is inside. So dimensions are roughly 10 centimeters from here to here, about 6 to 7 centimeters on this tube here. This section, diameter of the outer tube is 7 or 8 millimeters. I think I had 8 millimeters. Inner tube is 2 millimeters, and then you basically center this tube here, seal everything as well as best as you can. This one of course is static, so there are holes in here, so this doesn't matter in the sealing part of it. And then other than that, yeah, this juts out a centimeter or two outside, and then basically you get good. You should be able to get good readings from this type of a design. Next, we'll look into some measurements with the actual instrument, and I'll show you some pictures as well of the constructed instrument. So this first picture shows the main tube, which is the one that has the inner tube installed into it. The 4 holes have been drilled already, and on the left you can see the 45-degree angle roughly where I've connected the other tube and then soldered everything together. I used some copper wick to actually bind that and strengthen that connection over there. The small tube is shown below sitting on the table. This picture shows that copper wick which is wrapped around the smaller tube, and that's going to be pushed into the main tube and then soldered at that point. And here it is pushed into the main tube and then soldered and sealed. And this one is the other side of the Pitot tube with the tube coming out on the other end. And the next slide will show you that junction between the small tube and the big tube where I cut. So this is the fully constructed Pitot tube. The left side showing the dynamic input, the narrow tube going into the larger tube with the 4 holes around it, about 2 centimeters away from the end. And you have the two outputs, one the dynamic output which is going straight through to the, which has a junction between the small tube and the big tube, and then the bottom output is the one for the static pressure. This is one of many iterations that I used to connect the Pitot tube to the car. This is using Gorilla duct tape, which is very strong and can easily withstand the freeway speeds and it won't blow off. I also tried it installing it near the rear view mirror, and that also seems to work. But I think this was better because it's in free air, a little bit higher up on the car. So the final setup I used for the measurements. So today I'm going to do a test run with a homemade Pitot tube, which I constructed yesterday. And I was not happy with the one I had bought from Amazon, which was, I believe, was not accurate or leaking, so was not able to register accurate speeds or even any kind of speed at higher speeds of the car. So it was basically not responding to anything like freeway speeds like 65 miles per hour or higher. It was fairly okay at lower speeds like 25 to 40 miles per hour, but anything on the freeway it would pretty much not go above 50. So I think there's a leak or something in there. Anyhow, this one is a homemade one. Hopefully it's not leaky. I'm going to do a test run on the freeway today. The winds are roughly 2 to 3 miles per hour from the west today, and I'll be initially heading on an eastbound heading 65 on a freeway, and I will turn it on again when I get to the freeway. So now I'm heading towards the freeway at a little bit higher speeds. I'm doing 40 miles per hour. The instrument is reading 35 at this moment. There's going to be a bit of wind noise because my windows are slightly open to allow the tubes to go to the outside of the car where the Pitot tube is mounted, so you might not hear me that well. So I'm going to take the freeway entrance here. Initially I'll be going exit ramp and then on. Okay, so now it's 70 and it's quite pretty low, 50 or so. So I'm guessing again that there's a leak in this thing. The airspeed indicator is not active. So I'm going now eastbound on this freeway, and I cut out the audio because it's extremely noisy and you won't be able to hear me. So I ran this for a couple of miles and saw that the the ASI was fluctuating between around 45 or so to 760 or so miles per hour, even though I was anywhere between 65 and 70 miles per hour. So not particularly accurate. One of the things could be that I'm following another vehicle, and I realized later that that has a huge impact on the speed of the indicated airspeed, even though the car is, going at the same speed continuously. It's just that the air is disturbed to the point that it's not recording the speed very well. So that's something I'm going to check on somewhat less turbulent area, like a smaller road where I can still go reasonably fast, but not affected by other cars and other crosswinds and so on like that usually can occur on a freeway. It's definitely working fine at lower speeds, like 30 miles per hour, 40 miles per hour, but anything above 50, I would say, is suspect. So I'm not sure what is going on with needs some more investigation. So right now I'm doing a steady 45 miles per hour on this country road, and the reading is stable at around 38. Again, it's a eastbound, roughly eastbound heading. It'll be interesting to see what happens when I go westbound on the same road. If it does read higher or lower, definitely indicate a presence of wind. So I think this is a very good road to test this on, at least at lower speeds. Right now it's a steady 45 miles per hour. It's not fluctuated much. It's still at 38. What I'm going to do is to turn around on this same road right now, so the same environmental conditions, to see if there's any difference in the reading going westbound. It's right now very stable, so I'm quite happy with this reading. It's about 38 to 39 miles per hour. Okay. Okay, let's do 45 on this westbound heading. So it's reading 36 to 37. So we do have 1 mile or 2 miles per hour difference in the previous reading. So it's reading 35, 36 or so. It's definitely working. There is a sensitivity to wind. But I wish it would work at higher speeds. So back on the same road, going eastbound at now 45, 39 to 40. So to summarize this east-west run on this smaller road, I was seeing about like 40 miles per hour going eastbound, or 39, and 35 or so going westbound. So essentially, I think the wind was actually from the east, not west, as I was thinking. I looked at the weather reports in the local area at the airport, and it's basically there was no wind. So I'm guessing that there is some local winds that are, not being recorded. They are mild, or sorry, light and variable, I would say. And this is definitely being sensed by the car. As you can see, there's a difference, even though some of the weather stations aren't reporting it. So I think one of the critical things in for measuring wind or indicated airspeed or effect of drag or air on the car is to look at the local wind conditions like I'm doing right now. Okay, so I've cleaned out the tubes, and also I did a slight pressure test on the ASI. Blew some mild pressure, used the compressor to blow some air into it. Didn't I sent it, basically I pressurized it enough to read about 100 miles per hour, close to the maximum. Did it a few times, and now it seems to be settled at 0. I'm gonna see how it responds to at higher speeds. It seems to be smoother right now. At least it's responding fine. And I was able to see higher speeds when I was driving back from the original place I'd stopped. And now I'm gonna go back on the freeway and then do some measurement on the westbound direction at around 60-65 miles per hour. So we'll be entering the freeway shortly. Not much traffic, so we might be able to get to 65. Concerned about low speed and accuracy, but hopefully I would like to see better accuracy at higher speeds, about 50-60 miles an hour. So joining the freeway now at 60. It's reading definitely higher now at around 50 or so. So it's now I'm doing of airflow, which could possibly also affect the readings of the vehicle. Which is a good thing because in order to get some better mileage, your travel behind another car, but definitely helps. So I'm doing 70 right now. It's dusting for sure. Noise changing, so that indicates some dusting conditions. Varying anything from 60 to 60, 70 miles per hour, 60 to 70. The main thing is that these instruments are very sensitive, and some damping might be necessary. If it were electronic, we could do some damping electronically, but this is a mechanical instrument and it's picking up all the minor fluctuations of the wind direction, whatever that's going on. I'm going to stop the recording here, 70 miles an hour, so we'll be exiting here. What did I learn? Do-it-yourself Pitot tube was built and tested in real-world conditions. The device, when connected to an airspeed indicator, works well in a terrestrial environment at low speeds in non-turbulent conditions. At higher speeds with a lot of traffic, airspeed fluctuations are large due to pressure disturbances, air turbulence, and other non-idealities, not necessarily due to actual winds in the area, which is a problem because that significantly changes your accuracy and your means to measure the actual wind conditions. More testing is needed, but it can be a useful device if the ASI response can be damped, and airspeed is especially important for fuel-efficient vehicles like EVs or hybrids, where drag has a significant effect on efficiency, the other being temperature for EVs. Some calculations here. Let's assume the fixed and frictional related losses that are there, like also your energy consumption due to the electronics in your car, other accessories. It's about 140 watt hours per mile. And this is typical of most of the smaller mid-size EVs out there today. And if an EV used, let's say, a total of 250 watt hours per mile at 60 miles per hour, with a 10 mile per hour headwind, this energy needed would be approximately go to 290 watt hours per mile. So it's about a 40 watt hours per mile increase because of a 10 miles per hour headwind, which makes the car think it's going at 70 miles per hour. With a 10 miles per hour tailwind, similarly, the EV energy will decrease to around 215 watt hours per mile. And really, what we are assuming is the wind drag is proportional to the square of the speed, and we assume that the fixed energy consumption in the car is always fixed. So, in the case of a car which has 250 miles of range, currently charged to, let's say, typically 80-90%, most cars these days with 250 miles of range, 10 miles per hour headwind would decrease the range to about 215 miles, and this could be a problem. On top of this, temperature has an effect on the battery capacity, not so much on the driving itself, although cold temperatures does have increased the air density, which may also reduce range. But let's assume it's mostly the battery capacity, and that of course will mean that you cannot charge to the full capacity that you have in warm weather. So that could be actually an even more significant factor in your range reduction than the headwinds that you're experiencing. And you can control the fact that you can slow down when if you know you have a headwind, and that could be a solution to the problem. Another solution is, of course, you can follow in the slipstream of other vehicles, and this reduces the indicated airspeed as we saw in the video. And although it's debatable as to the real effect over a long term, because the wind was quite turbulent with the car following, and that might cause different eddy currents and crosswinds and all kinds of other weird stuff that causes your efficiency to go down as well. So I think we need some more quantitative measurements um, over a stretch of time or a stretch of distance to really come to a handle on that. So what are some ideas for the future? One thing that obviously came out of this video is that it might be a good idea to add an airspeed reading besides the current speedometer that we have, which is based on ground speed and GPS, whatever. So it just one can actually do this calculation if needed. And if this is done, then I think drivers can be more aware of the range reduction due to headwinds in cold weather, especially. This gets to be an even bigger problem. And when you have favorable winds, you can actually speed up a little bit without really losing your range, and you can get to your destination faster. Um, the implementation of these of an airspeed indicator with a pitot tube is always going to be a challenge, given that this pitot tube is a bit of a weird-looking thing that could be a problem in cars because you don't know how to install it properly, and it juts out and could be broken easily and things like that. So, but I think the overall electronics and the other parts of the system can be implemented fairly easily, given that the amount of computing power cars have these days, and they can get the solid state or sensors that can do the job of the airspeed indicator, which is this mechanical instrument. But other than that, I think the pitot tube is still needed, but it could be probably be miniaturized and made more optimized for a car application. Some cars already have these weather information that is being included in the range calculation, like the Teslas and perhaps other cars. But these are based on weather reports and wide geographical area, wind reports, and other things like temperature and maybe even terrain, whatever else is there, even tire pressures and things like that. So I think it's something that can be done with local information such as this one, with from the sensor in the car, it would actually be even more helpful. One last point is for non-hybrid internal combustion engine cars. They really don't care too much about this wind-related drag because it's already they're not terribly efficient in terms of energy consumption. So using a little bit more fuel is not going to be a big change in the fuel efficiency, going from 25 miles per gallon or 30 miles per gallon down to 27 miles per gallon. Whereas in an EV, this makes a huge difference. So yeah, not they don't have to worry about it. Plus, they have enough gas stations that they can fill up wherever they need to. So in conclusion, if you know that you have a headwind, slow down at least till we get these sensors on board EVs and hybrids. Thanks for watching.